So let's have a look at some complex analysis, and let's have a look at the identity for the modulus of e to the z quantity squared. Now e to the z here, where z is a complex number. So complex number, z equals, now let's write that in terms of its components, a plus bi. Now here, a is the real part of z, so a is the real part of z, b is the imaginary part of z, hence we've got this I constant here, and I is square root of -1. And here a and b, they are real numbers. So a and b are real numbers. So that's all the identities there. And also one thing we also need to note, that z is a complex number, hence it's in the complex plane. So that will denote our complex plane. Now what is e to the z squared? Now we can use information from here that we've got that to try and get to some identity for this. So as z is a plus bi, I can now rewrite this as e to the a plus bi. So let's write that. So I'm going to write it down here. So I've got e to the a plus bi modulus squared. Now one thing here, the modulus of a complex number, that can be written in terms of Pythagoras. So the square root of a squared plus b squared. So let's write that down here as well. So the modulus of z, that equals square root of a squared plus b squared. Okay, so that's a basic set out of a modulus. Now a plus bi modulus squared. Now as this is an exponential, that's a standard function, by identity of exponentials I can split that into 2. So now I've got modulus of e to the a, and then multiply that by the modulus of e to the bi, and then squared. So that is just by algebra, I can do that. Now e to the a, where a is the real z, so let's write it in terms of that. So this is equivalent to e to the real z, and bi, that is e to the imaginary z, b, but with the constant there. So I'm going to leave that as e to the bi. So that is what we can rewrite that as. Okay, now e to the real z is just e to the a. A is a real number, so this basically just becomes a real number, e to the a. So I'm going to write that down here as e to the a and leave that in its modulus. Now I'm going to take care of this e to the bi and put that in the modulus on its own. And I can split this identity of these modulus by my rules of algebra. So I can now write e to the bi and then square all of it. Now this is okay. This is would be a real number. So whatever a is, that's just going to give me a real number. E to the bi, I've got this complex constant here, I. Now what I can do is use Eulers' famous formula. So e to the bi, that would simply be, by, excuse the pun there, the b would then break down into cosine of b plus I sine of b. So that would be using Euler's formula. Now what I can also do from that, I can also use my modulus, because that's eventually what I need, and say the modulus of e to the bi is basically the square root of the real and imaginary part squared. So that will be cosine squared of b plus sine squared of b. That would take care of that. Now cosine squared of b plus sine squared of b, we all know is 1. That's a real famous identity. So square root of 1. So I can rewrite this now as e to the bi as just basically square root of 1, which is just the same as 1. So that we just know is 1. So now what I can do is write e to the a times 1 all squared. Now e to the a times 1, that's a real number, that's a real number. So now I don't need my modulus. So now I've got e to the a squared. So I can now just do a bracket. Now with the squared I can just bring that inside there. And then all I've got left is e to the 2a. Or I could write that as e to the 2 real, in this case, z. And that would be good enough for our answer. Okay, now if you like this video, please subscribe and like the video and check the link below. There is loads of complex analysis stuff on there for you guys to have a look at. Okay.